So in this video, we're going to be talking about chemical bonds and the types of chemical bonds. So first, let's talk about ionic bonds. Ionic bond is where a metal and non-metal chemically combine to achieve stability. And the way they do this is that the metal, it gives away one of its electrons, so that turns into a positively charged cation, and then the atom that gained it, which is typically a non-metal, that turns into a negatively charged anion. And the cations and the anions create an create like a force between each other, and they merge together due to the positive and negative cations and anions and the different charges. So that's how an ionic bond is formed. To achieve stability, the elements when doing an ionic bond have to follow the octet rule, and to do ionic bonding, we're just going to see some examples, and also we're going to be seeing some special cases. So let's look at our first example. It's between group 1 and group 6A. So group 6A is basically just group 16. It just doesn't compose of the transition metals over there. Okay, these are the metals, highly reactive metals, and these are the non-metals over here, the highly reactive non-metals. Let's look at some examples. Let's take the first one over here, which is lithium. So if we have lithium, and let's take oxygen over here. So oxygen has 6 valence electrons. So I'm just going to put it numerically. Lithium has 1 valence electron. Oxygen has 6 valence electrons. But here's the thing. If we were to add them together because of the chemically bonding, that would get 7. But we need 8, right? So how do we get it to be 8 and achieve stability? Well, one way we could do it is through doubling this. So I'm going to create oxygen. Okay, so this is how an oxygen atom looks like. The ones that are not circled basically means that these are free spaces where electrons can come in. And now I'm going to show a lithium atom. So lithium over here. And basically, lithium has 3. This is how lithium looks like, okay? It has 1 valence electron, and this has 6. This has 6 valence electrons, and this has 1. That gives a total of 7 valence electrons. But to achieve stability, according to the octet rule, we need 8 valence electrons. So what do? We get another lithium atom. So when we get another lithium atom, this gives another electron. This has 2 electrons, and this has 6. And then 6 plus 2 is 8. We have achieved stability. So we would compress this into this 2 over here, and this would just be oxygen. So in total, we would get this is how it would be formed. This is how the losing and gaining of electrons work from group 1 to group 16. So now let's move on to our second example. We're going to be doing magnesium and chlorine. So magnesium is located in group 2, and chlorine is located in group 7A, also known as group 17. So let me draw how magnesium looks on Bohr's model. So magnesium has the atomic number of 12, and we get 2 valence electrons. So now that we have 2 valence electrons, we're going to compare it to chlorine. Chlorine over here, chlorine has the atomic number of 17, and I really don't want to draw like all of that. So what I'm going to do is I'm just going to do chlorine. This will show the number of valence electrons, this circle over here. So 1, 2, 3, 4, 5, 6, 7. So don't get confused, this is just the valence electrons. So this circle is valence. Okay, so you see over here, magnesium, it has 6 empty spots. This has 1 empty spot. So if you have 2 over here and 7 over here, 2 plus 7, that's 9. But we need 8, according to the octet rule, to maintain stability in the compound. And in order to do that, we have to have another chlorine atom. So basically what that does is that it gives 1 valence electron here. So this removes 1 valence electron. And we need to give 1 valence electron to this one. So basically, it has 7, right? And now it's gaining 1. This also has 7, and it's gaining 1. So if we add 1, we get 8. And 8 is what we need for the octet rule because it maintains stability. And now we have the stable atom. And magnesium is stable because it lost its valence electrons. And now it has a full circle of valence electrons over here. So that's also stable. So now that all of these are stable, we get magnesium chloride 2. So this is how it looks like. Okay, so let's look at our third example. We're going to be using group 1 and group 7A, or also known as group 1 and group 17. We're going to be using lithium and fluorine. Lithium has the atomic number of 3, so 1, 2, 3. And fluorine has the atomic number of 9. So fluorine. Okay, so you see lithium, it has one valence electron and fluorine needs one valence electron. So it's going to give up this valence electron. So this can fill in, and when that fills in, lithium has now reached stable because according to the duplet rule, it needs 2 over here. And here, if you look at fluorine, according to the octet rule, it needs A. So now that it is given 1, both of them are stable, so we get lithium, fluorine. Our final example for ionic bonding will go to group 2 and group 6A or group 16. We're going to be using beryllium and oxygen. Beryllium has the atomic number of 4, and oxygen 8. So it actually needs 2 more, and since beryllium has 2, it can voluntarily give it up over here. So -1, and what happens is that when it gives up, beryllium maintains stability, and now these guys are being filled up, so oxygen maintains stability. So we get beryllium oxide. So these are a few examples of how ionic bonding works, and we also looked at a couple of special cases. In ionic bonding, the electrons in metals basically give up their electrons to maintain stability, and for non-metals, they gain the electrons that the metals gave up to maintain their stability. And in some cases, if it doesn't work, they just call in another one of their atoms, and that way they're able to maintain stability. So now we're going to be talking about covalent bonding. So covalent bonding is basically the sharing of electrons between one element and another. Specifically, it happens between nonmetals and nonmetals. The difference between ionic bonding and covalent bonding is that instead of losing or gaining electrons, it's actually sharing the electrons in the middle. And when it shares the electrons in the middle, that's what we call covalent bonding. By sharing the electrons, both elements are attaining stability. There are 3 types of covalent bonding. One is called the single covalent bond, then there's the double covalent bond, and then the triple covalent bond. Each doing with the number of valence electrons the elements give to each other to maintain that stability. So let's look at a single covalent bond. Let's look at an example of a single covalent bond. So we're first going to be using hydrogen. And the reason why is because both of them only have one valence electron. And basically, for a single covalent bond, you need one pair of electrons. They need to share one pair of electrons. So basically, that's just 2 electrons. So here, what happens is when they connect through the covalent bonding, it looks something like this. This is a single covalent bond, and it follows the duplet rule. And see, you could see over here that according to the duplet rule, it needs 2 electrons to be stable. So if you look at it, there are 2 electrons that are stable. Hence, it's maintaining stability. Okay, so now we're going to be looking at the double covalent bond. So we're going to be using oxygen in this example. In the double covalent bond, we need 2 pairs or 4 electrons in total in the middle, so it can maintain that stability. So in the middle, it should have the 4 electrons to maintain the stability and follow the octet rule. Oxygen has a total of 6 valence electrons, and when it has a total of 6 valence electrons, it looks something like this. And you can give this 2 away and this 2 away, or these 2 pairs. 4 electrons, and what happens is we end up with oxygen like this, and we end up having 4 over here like this. And you can see it follows it because there are 4 electrons, and there's 4 electrons here, or 2 pairs, and it follows the octet rule, meaning that it must have 8 electrons. So you can see 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. They're both acting to each other's gain. So we're going to be talking about triple covalent bond. This shares 3 pairs of electrons, or 6 electrons in total. So let's look at the example, nitrogen. Nitrogen has 5 valence electrons, and you can see over here I only put the valence electrons, not actually like the electrons located inside of it, okay? So like don't get confused over that, okay? So nitrogen, what happens is we have to share 3, so this 3 and this 3 can go in, so you get total 1, 2, 3, 4, 5, 6. So we get 6 electrons or 3 pairs, because 1 pair over here, 1 pair over here. So total 8 electrons are there, each one following the octet rule, meaning you have to get 8 electrons to maintain stability. And since 8 electrons are there, both are stable. And they found the triple covalent bond. This is the single covalent bond, and this is the double covalent bond. And if you didn't know, these guys, they all are non-metals. So this is all about covalent bond and the examples. And covalent bond, unlike ionic bond, shares the electrons instead of losing or gaining. It shares the electrons, so it can follow either the octet or duplet rule. And there are different types of covalent bonding, those 3 being single covalent, double covalent, and triple covalent bonding. So lastly, we're going to be talking about metallic bonding. Metallic bonding basically occurs in metals only, where they lose their electrons. And what happens is, when losing their electrons, all these electrons gather up, and all of those regular elements, they're now positively charged cations, meaning they have more protons than the electrons. And when you have positively charged cations, it creates the positive charge. However, the electrons, they're negatively charged, so it creates a negatively charged part, and basically you have 2 forces, and then they attract with each other and create a lattice type structure like this over here. It creates a lattice type structure, or like, if you want a better pictorial way, a cube like structure. So when the electrons, when they're like freely going around, we call this the electron seed theory, or delocalized electrons. These delocalized electrons are, because they're like moving very fast, they're really good conductors of heat and electricity. Hence, because the electricity and heat, they work on positive and these are negative, so the charge happens, and that's how it moves really fast. So that all makes sense now. So this happens only in metals, and an electrostatic force appears between the positively charged cations and the negative electrons, the negative group of electrons, and it creates that lattice structure that then we have metal sheets. So let me just show some examples. So iron has 2 electrons located in its outermost shell that it can easily lose. When it loses these 2 electrons, and when you have a group of these iron, basically this is what happens. You have a bunch of iron atoms. They're just sitting around, really just doing nothing. Iron has 2 outermost electrons, so each one will lose around like 2 electrons. And when it loses 2 electrons, instead of like sticking together, what happens is that these electrons, they just float around, and we call this the sea of electrons. And now Fe becomes a cation, or +2. Let me just draw it. Fe +2, meaning that now it's a ion or a cation, so it's positive. And now we have a bunch of these negatively charged electrons over here, because electrons are negatively charged. What happens is electrostatic force happens between the positively charged cations, or the iron, and then the negative electrons over here. This force creates a lattice structure, or like I could show it to you. So like we have one over here connected to like one over here, connects to like another one over here. So this is how the lattice structure looks like, and it goes even more, but this is basically how one unit looks like, okay? This charge has a bunch of these electrons just floating in it. This creates kind of like a force that keeps each other away at a certain distance, and this is how we create this kind of structure. And this is how the metallic bonding happens, create the iron sheets that we know. Conclusion, metallic bonding is where the element loses its outermost electrons in its outermost shell, and it turns into a positively charged cation, and there's a bunch of these negatively charged electrons. It creates an electrostatic force that causes the cations to create a cube-like structure, or a lattice structure, and the electrons float inside of it, creating a type of distance. Hence, it creates a metallic sheath, or an iron sheath, as we look at the example, and that's how we have metallic bonding. So to recap everything we have learned, ionic bonding happens between metals and non-metals, and it's where the metal gives away their electrons, and then the non-metals takes in that electron, and basically due to that electrostatic force, they come together and form stable compounds. Covalent's pretty similar. However, instead of giving away the electrons, they share electrons and follow the duplet or octet rule that way through sharing. And there's a single covalent bond, double covalent bond, and triple covalent bond, depending on the number of valence electrons it has. And then finally, we have metallic bonding, which happens when the element loses its outermost electrons in its outermost shell, and that creates a sea of electrons or delocalized electrons. And then basically there's an electrostatic reaction happening between the positively charged cations, or the elements that gave up their electrons, and in the negatively charged electrons. These negatively charged electrons and the positively charged cations create an electrostatic force, and that causes it to create a lattice structure or a cube-like structure like this over here. And with the electrons floating in between, it creates a kind of force that keeps it away, having a type of metal sheet that we know. This is all about different types of chemical bonding between ionic, covalent, and metallic bonds.